Okay, so question about the actual definition of rate, right? In this case, average rate. So rate of reaction, in any case, we measure it by measuring the change in the concentration of a species involved in the reaction over the change in time. That is the definition of the rate. Okay. Now, in this particular case, we're interested in the rate of reaction of NO2. What do we know about the NO2? Well, it decreased from 0.01 to 0.05 over 100 seconds. Okay, so let's color code that nicely. What's the change in the concentration of NO2? Well, it started at 0.01, it ended at 0.005. Any change is final minus initial. So 0.005 minus 0.01 happened over 100 seconds. That's the change in time. Now, this is the average change over that 100 seconds. We got no idea of not knowing. No idea about what's happening between 10 and 20 seconds or 60 and 70 seconds, but we do know over 100 seconds this was the change in the NO2. So punch that in and we get that it was minus 5 times 10 to the minus 5 molar per second, or moles per litre per second. Okay, so rate is always, as I say, change in concentration over change in time. So units of rate will be whatever concentration you're using, which we always use molarity, and then seconds, minutes, hours, whatever is the appropriate unit for time. Question 2 is much more of a question that goes to emphasizing that even though you study the rates of reactions, they're still subject to the chemical equations, they're still subject to the stoichiometry. So here in this rather complicated equation, 4NH3 plus 5O2, that means that every time you use up 4 NH3s, you must also use up 5 O2s. And when that happens, you make 4 NOs and 6 H2Os. So what that means is, of course, that because you're using up 5 O2s in the time you're using up 4 NH3s, you're using up O2 faster than you're using up NH3. And you're making water faster than you're making NO, because for every 4 NOs you make 6 waters. Now, express those relationships by just saying that we can talk about the change in concentration of anything over the change in time, and we relate them using these coefficients by normalizing it down to effectively if something had a coefficient of 1. So we divide the H2O by 6, we divide the NH3 by 4 to get it down to where we have 1. Now we just pop in what we've got. Change in water over change in time given 0.6. So throw that into the equation. 6 times 0.6 is minus 4 times concentration of NH3 over delta T. This minus sign here was there because, of course, NH3 is a reactant. Thus, its change is negative. Water is a product. Its change is positive. So we put that in the negative sign for the reactants in order to equalize the equation. So anyway, throw that in. And the change in NH3 over the change in time, minus 0.4. But of course, we don't want just the change. We want to know how quickly is it decreasing. Decreasing tells you, yeah, it's a negative. So we eliminate the negative because we're taking care of the negative with the word decrease, 0.4 molar per second. Very important thing to know about the rate of any reaction is the rate law. The rate law tells you how the concentration of the reactants affect how fast the reaction go. And of course, that's all tied into the mechanism and the slow step that we'll get to questions on later on. Right now, we're told that for this reaction, the rate is K times the concentration of H2O2 times the concentration of I minus, which means that every time we double the H2O2, we double the rate. Every time we double the I minus, we double the rate. Now, if you notice that the main reaction is H2O2, that's what we expect, that's I minus, but there's also the reactant H plus. Well, H plus doesn't appear in this rate law. Now, as we'll see later on, what that just means is that H plus isn't used until after the slowest step. So therefore, no H plus at all in that slow step. It's what's known as zero order. Overall reaction, well, it's first order in H2O2, the exponent there is 1. First order in I minus, the exponent there is 1, which means it is second order overall. Rate law, very, very important that you understand how it works. Question 4, again, rate law. Again, I tell you the rate law, rate is KH2 times NO squared. And then I say, well, what does happen to the rate when we change the concentrations? Well, that's the rate law. First thing we're going to do is we're going to double the h2. Well, here's h2, the exponent is 1. So whatever we do to h2, we do to the rate. Double the h2, double the rate. Now for our NO, we're halving the NO, and whatever happens to NO, the square of that happens to the rate. So if we're halving the NO, we halve squared the rate of the reaction, because the rate depends upon the square of the concentration of NO. Put all those together, we doubled the rate with the H2, but then we halved it with the NO, and that gives us an overall change of halving it. Okay, doubling the H2 doubles, halving the NO, well, half squared is quarter, so quarter's the rate, so when you double and then you quarter. So the next 4 questions all are associated with how do you actually determine the rate law. Well, one way that you do it, because the rate law is associated without changing the concentration, changes the rate, is you just do a series of experiments in which you measure the rate and then you change the concentration, and measure the rate and then you change the starting concentration and measure the rate, and so on. So we get a little table like this. Now there's 2 ways to do this really. The first way is by inspection. And so under nice conditions, you might say, well, I can see that going from this first to this second, I haven't done anything to A. I've doubled B, and then 0.085 to 0.17 is doubling the rate. So in other words, whatever I do to B, I do to the rate. So the order of B is 1. However, a lot of times you're under stress, or maybe the numbers aren't as nice. So what I prefer, certainly in exam conditions or when working through things, is to give you a standard format. So there's our rate. Law, rate is K, times concentration of A, that's one reactant to the power of X, times concentration of B, that's the other reactant to the power of Y. Note that the rate law doesn't have to have anything to do with the overall equation. I can't just say, well, there's 1A, so X is 1, there's 2 B's, so Y is 2. The rate depends on the slow step of the reaction, not the overall reaction. Well, anyway, now I've got my general rate law. I just throw in these data. So first set of data, the rate is 0.085, concentration at A 0.05, concentration of B 0.1. Again, raise the A to the power of X, B to the power of Y, because those are my constant but unknowns. And then throw in the data for the other 2 experiments. Okay, so now I've got 3 equations that have 3 unknowns. So I can combine these equations to get rid of hopefully 2 of the unknowns, and that will allow me to determine the last one. So the first thing we'll do is go back to what we noticed before. If we look at equation 1 and equation 2, K is the same, 0.05 to the X is the same. So if I divide these through, the K's cancel, the 0.05 to the X cancel, and I'll be able to figure out what Y is. For a calculational tip, always put the bigger one on top. So I'm going to divide equation 2 by equation 1, because equation 2's got the number that's bigger than equation 1. So that's what it looks like. Left-hand side becomes 2. Right-hand side, I cancel out the K, I cancel out the 0.05 to the X. I get 0.2 over 0.1, both to the Y, which becomes 2. 0.2 divided by 0.1 is 2, raised to the Y. So if 2 is 2 to the Y, Y must be 1. So we know it's first order for B. So now every time we see a Y, we can just think of it as 1. Now what I'd like to do is get rid of everything but the X's. Now of course I don't have an equation in which I can cancel out all the Y's, but that doesn't matter because I know what Y is. So we'll take equation 3 divided by equation 2 because the X part changes from those. I get this, cancel the K's. Now I get the left hand side becomes 3. Here's 0.1 over 0.05, which is 2, so 2 to the X. And then 0.3 over 0.2 is just 3 halves, or 1.5. So now I can rearrange that a little bit to get X is equal to 1, okay? Because I take 3, I divide it by 3 halves, I get 2. 2 equals 2 to the X. X is equal to 1. So now my rate law is rate is K times the concentration of A to the power of 1 times the concentration of B to the power of 1. Let's do another one. Same idea, same process. I'll put it all up and make sure you see what we're doing. First of all, we know our reactants ICl and H2, so that's what's going to be in the rate law, ICl and H2. We don't know the X, we don't know the Y, so we have to use these rate data to get that. And so I just take the data that I've got, which are rather nasty looking, all these times 10 to the minus 7s and so on, throw them in to this general rate law equation, and now I'm going to solve. So which one shall I pair up first? Well, now this is actually a much nicer set of data, because if we look at experiments 1 and 2, everything except the ICl changes, and if we look at experiments 2 and 3, the ICl is staying the same and the H2 are changing. So I've just got to combine those two pairs to figure out my X and my Y. So let's do 2 over 1 because 15 is bigger than 3.7. Throw everything in, that's what I get. Cancel out the K's, which cancel out the 1.5 to the Y's. Left hand side of this becomes 4. Right hand side, 3 over 1.5 is 2 raised to the power of X. So what do I have to do to 2 to get it to 4? X must be 2. So every time I see an X, I now know it's a 2. Now let's go ahead and do 3 over 2. And notice I've replaced the X in these original ones by the 2 that I know about. Cancel out the K's, cancel out the 3 squared. Left hand side becomes 3. Right hand side becomes 4.5 divided by 1.5 is 3 to the power of Y. Thus Y must equal 1. So the overall rate law, K is ICl squared times H2 to the 1. So the overall order, it's second order in ICl, first order in HCl. 2 plus 1 is 3. This is one of those where coincidentally the exponents in the rate law equal the coefficients in the reaction. But as I said before, that is not, absolutely not always going to be the case. You can never assume it until you see that it's the case when, oh, I've done my rate law, see how it matches up. Another one, question 7, using the data to determine the value of K. Well, we've overlooked K, haven't we? We've always cancelled it out. And that's not a bad thing because, of course, as I say in the videos, K is not a very good constant at all. It changes with temperature. The rate law, however, the orders, don't change with temperature until you completely change up the reaction, which usually doesn't happen. So K, terrible constant, we usually don't bother to work it out. But there are times in which you need to know K. So let's just figure out how to get K here. And this is a much simpler reaction because we've only got one reactant. So rate law is K times the concentration of that one reactant, N2O5 raised to the power of X. Throw in our two sets of data. Now I'm going to divide 2 by 1 because you've got to watch out for these powers here. This is 2.25 times 10 to the minus 1, which is bigger than 4.5 times 10 to the minus 2. So pop that in. Left hand side becomes 5. Right hand side becomes 5 to the X after the K's cancel. So X is equal to 1. So we know the rate is K times the concentration of N2O5 raised to the power of 1. Now let's throw in the data to determine K. Rate is 4.5 times 10 to the minus 2. K we don't know. 2.56 times 10 to the minus 3 raised to the power of X. K is 17.6. Whenever you're asked for K, always get it from as many equations as you can, because just because it works for one equation doesn't mean that you haven't messed up the calculations and it doesn't work for the other equations. So let's take equation 2, do that same determination. K is 17.6. Life is wonderful. I am so happy. Units of K are per second. How do I know that? Well, first of all, I know it because it's a first order reaction, and I know that for any first order reaction. But you can also have a look at it just from the equation. Rate is molar per second. Concentration is molar. So K must be per second, 1 over seconds.